This presentation will explain how a fiber Bragg grating system works, and then show a simple demonstration. An FBG is an optical filter made up of many fringes, written into the 9-micron core of a single-mode optical fiber. It is created by interference between two beams from a high-power UV laser. The FBG is a periodic variation of high and low refractive index. Fresnel reflection occurs at each of the thousands of refractive index boundaries along the FBG. These all add together at one unique wavelength, the Bragg wavelength, which is tuned to the period of the grating. The Bragg wavelength is reflected, all other wavelengths are transmitted. An FBG can be written at a certain Bragg wavelength by adjusting the period of the grating, the distance between the fringes. Each FBG reflects a unique wavelength which is tuned to the grating period, and passes all other wavelengths. Now, if the fiber is stretched, the period length increases, and so the reflected wavelength increases. Or, if the fiber temperature increases, then the period refractive index increases, meaning the optical path length between the fringes increases, and so the reflected wavelength increases. So, by precisely measuring the reflected wavelength, we can detect tiny changes in the strain or temperature at each FBG. And, by writing multiple FBGs at different wavelengths, we can make a distributed array of strain and temperature sensors on a single fiber. Let's have a look at how this works. Here's a fiber with an array of FBGs at 5 separate wavelengths. The reflection spectrum shows 5 peaks reflected at 5 wavelengths. If you take a reference at that point, you see 5 equal temperature points at the 5 FBG locations. Now, if you apply heat to the fiber, look what happens to the spectrum. The FBG wavelengths all increase, more in the center where the heater is closest, less on the ends. Using the thermo-optic coefficient of 10 picometers per degree C, you can see the temperature changes on the lower graph. Now let's look at strain. Here's the same 5 FBGs array. It has the same reference spectrum. This time we are measuring strain, so our wavelength reference is set our 0 strain position. Now, if you apply strain to the fiber, look what happens to the spectrum. Where compression is applied to the left of the fiber, the wavelengths reduce. Where tension is applied to the right of the fiber, the wavelengths increase. Using the stress optic coefficient of 1.2 picometers per microstrain, you can see the strain changes on the lower graph. There are 4 components to a FBG sensing system. Firstly, the FBG sensor containing a fiber with one or multiple FBGs. Secondly, the FBG interrogator which can simultaneously read numerous FBG arrays. Thirdly, a processing unit which converts the Bragg wavelengths to measurements of interest. Finally, advanced software to further process the data, then store or visualize the data in a convenient format. Here is a typical display from Proximion's temperature monitoring software. The main display shows the spectrum from one fiber containing 70 FBGs. The lower display shows the amplitude of the FBG peaks. The small peaks on the right are an optical barcode which contains the sensor serial number and calibration information. The right-hand display shows the frequency of each FBG reflection, from which the temperature at each FBG location can be derived. The calibration table for the FBG array is used to convert each FBG wavelength into temperature. The result is a temperature profile along the length of the temperature probe as shown on this tab of the software. Here you can see a video of the system in action. The display in the background is the temperature profile. As you can see, the probe is at room temperature. In front of the screen you can just see the probe itself. It is an FBG array inside a thin steel tube. You will see that the operator's finger temperature is picked up as he runs his fingers along the probe. Then you will see the system picking up local temperature events from a heated wire which is briefly touched to the probe. We hope that you found this presentation interesting and informative. If so, please get in touch to discuss your own fiber optic sensing needs. You can find all our contact information at proximion.com.